So this is our third lecture in vapor power cycles. We started off with the Carnot vapor power cycle, and then we moved into the Rankine. We'd had superheat, reheat, and today we're going to talk about regeneration. That's a very funny term, regeneration, but basically the only thing I'm going to talk about is the open feed water heater. Next time I'd like to talk about a closed feed water heater, and I'd like to also talk a little bit about pump and turbine efficiencies, which we've avoided up to this point, but you can definitely add that. It's no problem. So we have our cycle here. We already talked about superheating it, coming out of the steam generator, and then passing it through the first turbine, and then maybe taking it back for reheat. Then going through a second turbine stage, and those help improve the efficiency. There's reasons we do that to help the efficiency, but what we want to do is we want to think about the challenge of having such cold feed water coming into the steam generator, and we know that that's not efficient. That's a source or an opportunity to improve the efficiency. So how can we get this water right in here that's coming into the steam generator hotter? Well, burn more fuel. Well, no, we want to avoid burning a precious fuel. We want to get it hotter without burning more precious fuel. So how do we do that? Something's going to happen right in here to heat it up without burning more fuel. Now you may think about, well, maybe we use solar energy. No problem. You could do that, but in the scope of this, any energy into the system is expensive energy. If you want to do a senior design project and try to do some renewables with solar energy, fine. That's where you could plug it into the system, and it would work. It would help. But let's just take a look at a conventional. So what we introduce is what we call an open feed water heater. We've talked about these heat exchangers before. You can have mixing type heat exchangers, and that's what this is. It takes an inlet fluid stream and inlet fluid stream, so two inlets with one outlet. That one outlet's going to be warmer than if we would have just taken and not had that open feed water heater. Okay, well, where do we get this fluid stream right here? Well, we take a fraction of what comes out after the first turbine, and before we send it back, we don't send it back actually to reheat, that would be expensive. We take a fraction and divert it down to feed the open feed water heater. You think, that can't help. Yeah, it does, it really does. You have to run the numbers and you'll see, oh yeah, you'll get a bump up in thermal efficiency of the plant by doing it this way. I mean, it's like taking out of the right pocket and putting it into the left pocket. How does that help? But it does. Okay, and then the reheat continues, but we don't reheat 100% of what went through that first turbine. We only heat a fraction of it because some of it's been diverted. And then it continues here, and now what we see is what was diverted joins up with what continued in the cycle, and now we're back to what goes through the steam generator and into the first turbine. So let's take a look at the new device that we had to introduce. We had to introduce an open feed water heater. What else did we have to introduce? The second pump. The second pump. And so I'd like to talk a little bit about pressures. Okay, we've studied these open heat exchangers, these mixing heat exchangers before. Does the heat exchanger change the pressure of our fluid? That's a key observation you need to make right now. Okay, so think about it. We have the pressure at state 6 and the pressure at state 7. Is there any difference between the pressure at 7 and the pressure at 6? No, that's a key observation. If you don't make that observation, you're going to be really hard to analyze this system. And then we think, okay, the pressure at 2 is right up here. And it's lower than the pressure at 1, isn't it? Because as we go through the turbine, there's a pressure drop. But what about the pressure at 2 compared to the pressure at 6? Is that the same pressure? They have to be. They have to be the same pressure. So what you have is you had an inlet to a heat exchanger, inlet to a heat exchanger, and outlet. This is state 7, this is state 6, that's state 2. They all have the same pressure. You can't have one high pressure and two low pressures. That doesn't make sense. You would have to have maybe a throttling valve in there if you think, oh, here's two. Well, then that's not coming in. There's some modified state if there's a throttling valve. But there's no throttling valve. This is just an open pipe diverting a fraction of the flow down. Okay. So right away, P2 is equal to P7 is equal to P6. Heat exchangers don't boost the pressure in our in the systems or drop the pressure. What boosts the pressure? Pumps. What drops the pressure? Turbines. Is there a difference between the pressure at 8 and the pressure at 1? It goes through the steam generator, it's heating it up. No, it's the same pressure. We have to work through our pressures and get them right. Okay, the other thing that we have to work through are our mass flow rates. So before we do an energy balance, let's do our mass flow rates through this system. What I'm going to do is I'm going to make a big pen, maybe like right here to make it more visible. So what comes through this steam generator goes through the first turbine and stops right there, and then there's a split, isn't there? There's a split. So I'm going to change color. I'm going to say that the blue fluid stream goes for the reheat. And for a lot of calculations, you're going to find that that's 75% or 80%. It's a large fraction of what went through the steam generator through that first turbine. But it's not 100%. It's about 70, 80%. Think about that. So it continues on, and it's what passes through the second turbine. Only 80% of what went through that first turbine goes through the second turbine. And then it goes through the condenser. Then it goes through the first pump, and then it goes into that open feed water heater. What was diverted down to feed the open feed water heater, I'll try and draw it this color, green maybe, comes down and mixes in. Okay, well, if that was maybe 20% and 80% continued to reheat, second turbine, condenser, first pump, don't they join back up in that open feed water heater? And aren't they back to 100% that goes through the second pump and then through the steam generator? So when you analyze it, you may talk about, let's say, mass flow rate that goes through the first turbine. You see that syntax? And you know what? That's the same as the mass flow rate that went through the second pump. You see that? The flow rate through the second pump is the same as through the first turbine. Okay. And then maybe we think about the mass flow rate that goes to the reheat. That's what's going back this way, through the reheat. Mass flow rate through the reheat. Well, that's the same as the mass flow rate that goes through the second turbine, the same as the mass flow rate that goes through the condenser, the same as the mass flow rate that goes through the first pump. It's all what I sketched in blue. And then for the green, there's only really one. I'm going to just say it's the mass flow rate of the fluid that's diverted to feed the open feed water heater. It's that little green. It's like if I wanted to go back and do my color coding, this is kind of the green, this is the blue, and this would be like the red. Right? All right. Well, it's very natural to talk about these as in terms of fractions. I already did that. So what they'll have is they'll have a symbol Y. I'm sure they looked around and said, oh, let's talk about the fraction of flow that's diverted after the first turbine down to the open feed water heater. And they struggled with what symbol to give it. And they picked Y for this textbook. Y is a mass fraction. It's defined as what goes down to feed the open feed water heater divided by what went through that first turbine. And again, an example would be, oh, that's about 20%. And then 80% continues. So a lot of times they'll have Y in parentheses to emphasize this is some mass fraction, not a new property, not a new state. It's some mass fraction. And then this is 1 minus Y going this way. And this is 1 minus y going through the condenser, and 1 minus y, going through the reheat, going through the second turbine, 1 minus y going through the pump. And when they join back together, 1 minus y plus y gives you back to 100%, 100%, 100%. So mass flow rates, mass balances, mass fractions, that's pretty easy, but we're going to use that symbol y in a minute more. It'll be key to analyzing the problem. Okay, ready to press on? Here's a question. I'm about ready to feed some fluid into pump 2. Hey, we've studied pumps before, right? Okay, for state 7, isn't that the fluid state that's coming into the pump 2? You're a design engineer. Do you think state 7 should be subcooled liquid? Do you think it should be saturated liquid, a two-phase liquid vapor mixture, saturated vapor, or superheated vapor? Your choice. You're a design engineer. What should it be? Saturated liquid. Pumps do not like any vapor with it. They like liquids, and the warmest liquid would be the saturated liquid. If it was subcooled, well, we're trying to get it warm before we send it through. It wouldn't be optimal for the system's performance. So that's a key observation. Because guess what now? We can basically get an equation for how large y needs to be. What is that fraction that needs to be diverted? We don't want to divert too much. If we divert too much, it's going to come out some superheated or some two-phase liquid vapor mixture. Not good. We don't want to divert too little. It'll come out subcooled liquid. We want to divert just the right fraction, so 7 is perfect for our pump. So we already did the mass balance for a control volume around the open feed water heater. It's almost too simple. Let me write it out again. We have the mass flow rate that's diverted to feed the open feed water heater, plus the mass flow rate, and there you could put a bunch of these. You could put, oh, it went through the reheat. Oh, that one went through the second turbine. Oh, that went through the condenser, or that one through the pump, whatever. Let's put goes to the condenser is equal to the mass flow rate that goes into the second pump, or the same. You could put a number of different things for both of these here, right? Okay. And then we also have an energy balance. We could write for this same control volume, steady state, no heat transfer with the surroundings, no shaft work in or out, negligible changes, kinetic potential energy, and we find that we have the inlet enthalpy at 2 with the mass flow rate of the open to feed the open feed water heater plus the enthalpy at 6 times the mass flow rate coming from through the condenser, through the first pump, is equal to the enthalpy at 7, the mass flow rate going to the second pump, or what did I write? Did I write second pump? Let's put the first turbine stage, because it's the same as what goes to the second pump. Okay? So what we do is, you can rearrange this a number of different ways, but if I take and eliminate, let's say, the mass flow rate through the condenser right here, I'll get an equation H2 mass flow rate open feed water heater plus H6 times mass flow rate through the first turbine stage minus the mass flow rate open feed water heater equal to H7 mass flow rate through the first turbine stage. Did you see the math there? 2 equations. I eliminated m dot through the condenser. And then we take both sides of the equation, all terms, and we divide by the mass flow rate through the first turbine. And then you say, oh, this is H2 times Y. Remember our definition of Y? Y was the mass flow rate to feed the open feed water heater divided by the mass flow rate that came through the first turbine. Oh, that's just Y there, plus H6 times 1 minus Y equal to H 7. This is an equation for the fraction y. And so what does the equation y give us? Will it be H7 minus H6 divided by H2 minus H6? Let me pause. Is there an error?
So is this going to be true for every open feedwater heater?
You have to be careful on that. This is a system that only has 2 turbines. I could have a system with 4 turbines, 2 open feedwater heaters. You have to look at each case. The key is I bring just enough down such that state 7 is where I want it to be. State 7 is saturated liquid because it's going into a pump. Yeah, so don't, you have to really look at each system and maybe a slightly different equation. All right. So I was going to derive that on this page, but I think there's the equation. I derived it on that same page. Okay. So this is the equation for y. How did we get it again? Mass balance and energy balance around the open feedwater heater with the criteria that we want state 7 to be saturated liquid. Okay. All right. Now there's going to be another thing that's a little, when you're first introduced to it, you think, what are we doing and why are we doing this? It seems very confusing. But as an engineer, we're very interested in precise and accurate bookkeeping. We have to track all of our energy and energy flows. And we like to work on per unit mass basis. But now we have split our mass flow rates. So let's jump into this a little bit. Here, focus on this. What is the heat transfer from the working fluid? Don't worry about the negative sign. Positive from the working fluid, passing through the condenser to the cooling water. So usually you have some lake cooling water coming in, and so we're interested in this lowercase q. It's how many kilojoules of heat are transferred out of the working fluid to the quote-unquote lake cooling water or river cooling water per kilogram of what? Per kilogram of working fluid going through the condenser. That's not a hard question, right? So you do an energy balance right here. Leave the red line out, and it's just Q going to the lake cooling water. You could put the cooling water in the control volume, but I just want to put Q as out of the working fluid in the condenser. Okay. You do that control volume right there, and you'll find that this is equal to H something minus H something. What are the subscripts on these two H's? H4 minus H5. You've done enough energy balances, true? You're getting good at them. You don't have to start from, the most fundamental equation and then strike terms. Now, if that seems like, oh boy, do I have to memorize that? No, now you need to go back in Thermo 1 and start from the first principles. But after a certain point, when we get to college, it's like 2 plus 2. I'm not going to slow down and do this on my fingers and toes every time. All right, okay, so good, we got that, right? But now the challenge, because somebody wants this not per kilogram of steam entering the condenser, but somebody wants it per kilogram of steam entering the first turbine stage. You say, why would they want it? It'll be better for bookkeeping, trust me. And we're interested in bookkeeping all of our energy transfers in this system. So if we get all the energy transfers per the same mass transfer, it'll help us. So you're saying this is the mass flow rate through that first turbine stage, isn't it? And now you want this Q not in terms of per kilogram that goes through the condenser, but you want it in kilojoules per kilogram that goes through the first turbine stage. How would you do that? The units will guide you. If I took and multiplied the kilogram going through the condenser versus the kilogram going through the first turbine, wouldn't the units cancel, and I would get what I want? That kind of guides us. So we're looking at this is our original Q. This is H4 minus H5. That has units of kilojoules per kilogram going through the condenser. If I take that original and multiply by 1 minus Y, I will get a new Q. I'm going to put an asterisk on that Q to distinguish it with the Q without the asterisk. And this has the kilojoules per kilogram that go through the first turbine. Again, let's look at the units. Kilojoules divided by kilogram that go through the condenser, and then 1 minus Y must be that ratio of mass flow rates. 1 minus Y is how many kilograms go through the condenser divided by the kilogram that goes through the turbine. Think again about maybe this is Y is 20%. What is 1 minus Y then? 80%. So that means for every 1 kilogram that goes through the first turbine, 0.8 kilograms go through the condenser. Sometimes it helps to put numbers on it. For the example of 20%, so if I did have 1 kilogram or 1 kilogram per second, if you're thinking about flow rates, either 1 kilogram through the first turbine, 0.1 goes down to feed the open feed water heater, and 0.8 kilograms goes through the condenser. Right? So 1 minus Y, it has the units of either mass flow rate to go through the condenser divided by the mass flow rate through the first turbine, or you can just think about mass that goes through the condenser by mass that goes through the first turbine. Either ratio of kilograms or ratio of kilogram per second. Okay, so you ready to tackle a big problem? Hopefully in the time remaining we'll have enough time to tackle a big problem. So you're given a word problem. Let's read it. We have water is the working fluid in a regenerative vapor power cycle. That word is funny. You know, I didn't write the book. I'm just trying to clue you in on it. That basically means you have a feed water heater. That's a regenerative. Before it gets into the steam generator, so cold, we're going to warm it up. Okay. Superheated vapor enters the first turbine at 8 megapascal and 440 degrees C. Very similar. We've solved problems like this. But now it exits that first turbine at 1 megapascal. Whenever you have a feed water heater, you're going to have 3 pressures in the system. You know, one at the intermediate pressure. In this problem, it's 1 megapascal. That's the pressure of the open feed water heater. Okay. Some steam is extracted to the open feed water heater, while the rest is reheated to 440 and then enters the second turbine. Saturated liquid leaves the condenser at 20 kilopascal, and saturated liquid leaves the open feed water heater. Okay, then it just asks some two little things, you know, like, oh, what's the back work ratio? Get that maybe calculated in one line. You cannot calculate the back work ratio in one line. You may not even be able to get it in one page. You may need 2 or 3 pages to make that calculation, right? Some students always ask, how many questions on the exam? I can make an exam question, put this. It'd take you all day, right? So it's always in the complexity of the question. And then the thermal efficiency for the cycle. These are big, big questions. They're going to take a lot of work. Well, before we jump into it, what's our plan? What's the procedure? I outlined this last time. What should you do first? Okay, you're my volunteer for the first step. What is it? Get a sketch. Get a sketch of your major components. Are you going to have a steam generator? Are you going to have 2 turbines? Are you going to have 1 condenser, 2 pumps, an open feed water heater? And then the pipes to connect those components, And we don't talk about states in the middle of the condenser or in the middle of the turbine. We talk about the states between these components, don't we? So get a schematic of the components and clearly identify your states. Where are these locations? And they're going to be between the components. Make sense? You helped me on part 1, so somebody else for part 2. What's the second step that I recommend as you approach this problem? Yes, sir. You're jumping a little bit ahead. Property diagram, and then you're going to get that. So that one. So what property diagram is the best? Our temperature entropy. You can get a PV, you can get a pH, you can get a lot of them, but the temperature entropy is really insightful because when we go through the turbine, if it's a perfect turbine, no heat transfer, reversible, what is isentropic? Straight up and down on a TS diagram. Same with the perfect pump. Straight up and down on a TS diagram. Okay, so we like those TS diagrams. It's a challenge to get those states located on a TS diagram. But if you do, I think you're well on your way to solving this problem. Then the next is, thank you very much, step 3, get a table of what? Properties. Make a list of all your properties. You could say pressure, temperature, quality, enthalpy, entropy. Even if you were doing an exergetic analysis of this problem, you could put flow exergy as a column of properties for each of our states. So if you have 10 states and you have all these properties, that's a lot of data. Some of that data is given in the problem statement. 8 megapascal, 440 degrees C, 1 megapascal, 20 kilopascal, 440 degrees C. You can start filling in those property. And then you remember your state principle. 2 independent intensive properties fix a state, allow me to calculate, using the tables typically, other properties. So maybe I know pressure, temperature allows me to get enthalpy, entropy. Maybe I know pressure, entropy, I can get enthalpy, quality, etc. So you start working through the table, filling it up. The next one, we're trying to get to our backwork ratio and thermal efficiency. Another table, right? Another table of all of our energy transfers. Now this table is going to be more important than it was before because we're going to be interested in the work and the heat transfers, but I recommend you put a column for the traditional per kilogram that goes through that component, and then you put a column of Q asterisks and work asterisks. I don't think the book uses that notation, but a separate column for how much per kilogram that goes through the first turbine stage. Normalize everything to the first turbine stage so that when you do a sum of the Q's, don't do a sum of down the column of this Q and that W, but do down a column of Q asterisks and work asterisks. That will match. You have to work a problem for that to make sense to you, okay? All right. And then finally, you can compute your backwork ratio and thermal efficiency, especially using the data in the components of the transfers, which needed the data for the properties, which really you need to understanding where the states are, etc. All right. So this is that problem. I'm going to pause. I'm going to give you a handout, a piece of paper, and we're just going to work through it today. Okay? So I'm going to hand out some paper. There's some people immediately said, all the states are going to be on one of 3 pressure lines. This is my 8 megapascal pressure line. Does the 8 megapascal pressure line end there? No, it continues on. It's tucked in very tightly in that subcooled or compressed liquid region with the 1 megapascal line. Maybe I should change this size, make it a little easier to see. So this is my 8 megapascal line. This is my 1 megapascal line. And it's right on top of that, or right so close, I'd have to get a magnifying glass to get in there and see the difference. But they are different, but they're so close. They look on top of each other in that compressed liquid region. And then the 20 kilopascal line like this. A number of you did that. That was perfect. So now we look and we say, okay, well, where's some of our states? Well, state 1 was at 440, 8 megapascal. If you had a ruler, you can get that very accurately. You know, a straight edge. And a lot of people were doing that. I encourage you to do that. And then it went through the first turbine. The best turbine, it's reversible, adiabatic, isentropic expansion, straight down. Most people were pegging it right at high quality, but in the two-phase region. So that's state 2. Then you had to reheat back here to go through the reheat. Well, that's going to be adding heat, and it gets back up to 1 megapascal at 440. So that's where state 3 is. You're back up to that high temperature again of 440 degrees C. Then we expand, and we're at high quality. Maybe it's 78 or 98 or 97 or 95%, but it's still high quality. This is what comes out of that second turbine, and that's what goes into the condenser. Well, what's the condenser do? You have to know what comes out of the condenser. It feeds into a pump. It needs to be saturated liquid. So it's way over here. Isn't that state 5? And then we put it through the pump. And this is where some students have trouble, but it's a reversible pump. It's an adiabatic pump. It's isentropic compression. Constant S. Just like these were straight lines down, it's a straight line up. But it sure doesn't have to go very far, does it? To get to the other. And so right there is state 6. You typically use an arrow and say, hey, it's basically on top of state 5. And we had the whole discussion. When I zoomed in on real data, looked at pump and different conditions, maybe it's 1/3 of a degree C higher, 1/3 or 1/2 of a degree C higher. You can't see that on this scale. All right, but it's a little higher temperature, same entropy. That's state 6. It's at that higher pressure. What pressure is this? This is at 1 megapascal. So then what comes out at state 5? I'm not 5, 7. It's saturated liquid at that 1 megapascal. So where is that? Right there. Isn't that 7? And then the same analysis. Here's a great pump. It's reversible, it's adiabatic, hence isentropic, constant S. Where is state 8? I'm sorry, did I lose you?
I just had a question. Are
Sure.
we always going to assume that it's like isentropic?
No.
No?
But at this point, the problems are so long that if I start putting efficiencies into the turbine and efficiencies into the pump, which you've already mastered in Thermo 1, then it just slows down the calculation. And I'm going to have a hard time finishing this problem in an hour and 15 minutes, so I'm trying real hard. Yeah. It would just, what I found is it doesn't add anything. It just makes more work. Yeah, it's still adiabatic. Right. We will solve some of them, but not today. This right there is where state 8 is, right on top of state 7, but now it's at a different pressure. Maybe 1/2 degree C higher temperature. That can't be seen in this diagram. And then I use the diagnostic state 9. That would be right there. You don't need to put it in. The diagnostic state 10, which is saturated vapor, that would be right there. You don't have to put it in. But that's our states. Now we're ready to actually fill in the property tables. So I'm going to switch to another slide. You have this in your handout filled out now. And what I ask you to do is do the pressure first. That's usually the easiest. You can, it's one of 3 pressures. There's not 4 or 5 pressures for this whole thing. It's either 8 megapascal or 1 megapascal or 20 kilopascal. That's it. So you could fill in all those pressures, that whole pressure column, and then start percolating the temperatures and other properties. Okay? How far can you go? Well, I wish I could give everybody enough time to work it through, but I know I'm going to run out of time. So basically, state 1 is the highest pressure. But state 2 is after that turbine. You're already down to 1. Then it's through the reheat. And then after state 4, you're back down to the lowest pressure. And then 5. But the pump boosts it up, doesn't it? And then stays at that pressure, comes out of the open feedwater heater. And then it's after the pump. And then these are just diagnostics to help us understand where the heat transfer is. I make a column over here of things to help me. It's like, oh no, this fixes the state. I know the pressure and temperature were given. Knowing the pressure and temperature, I can get the other properties, bingo, right here in the table. Right? And then, what is this telling me? It's a little note to myself. I'm saying, state 2 is fixed by knowing the pressure and S. How do I know S? That's right, isentropic expansion through that turbine. So I just copy down this S, and I know this pressure, that S. We did this before. Get the see if it's in the two-phase region. This time it is, and so we can calculate our quality. And then using our quality, calculate the enthalpy at state 2. All right. I really want to get to the other table, so I'm going to really talk a little faster than I think that most can write notes. Sorry. But I want to finish this problem today. Otherwise, I'll leave it hanging. So then we reheat back to 440, don't we? And then these are just looked up as a function of pressure and temperature. Then it's the same thing. Copy down the entropy and get the quality. And if you actually did it with a ruler on our TS diagram, you'll see, oh yeah, that quality is slightly lower than the previous quality. The quality at state 4 is 96%, where it was almost 99% of the other one. And then you can actually check, these are the saturation temperatures. You could get the enthalpy as a function of quality. Saturated liquid, well, this is just H of F, isn't it? H of F and S of F if needed. I don't think I need that S of F. It's extra. The real critical column is my enthalpies. I'm trying to get all those enthalpies. Okay, so when I put it through the pump, I need to get the enthalpy at state 6. That's going to be the enthalpy at state 5, either plus or minus, depending if you calculate the work that the pump puts into the fluid as a positive or negative. So the work that the pump puts in to the fluid is the specific volume of the saturated liquid coming into the fluid, V sub 5, times the change in pressure, P6 minus P5. We've used that equation. It is used repeatedly in our textbook and example problems. VDP, VDP, VDP. That's for our reversible work. Somebody already asked, what happens if I have isentropic efficiency for the pump? Well, I'll have a two-step process. I'll have to divide that term by the isentropic efficiency and find the actual work put into the pump is even higher. But this is my minimum work, the lowest work. Okay. So then I boost that, and you could see that it's up about 1 kilojoule per kilogram. It's not a whole lot of work. Pumps are very efficient at boosting the pressure. Okay. That's how we get this H. Okay. Saturated liquid, this is H of F. I really don't need the S of F, but it's written in the table. I get the specific volume, and I do the same thing through the next pump. This is 7 to 8 is through the second pump. There you could tell, oh, it's a little bit more work per unit mass. And the next table will have that same number put down. And then these are just diagnostics. You could put them in there if you like. Okay, but I needed these enthalpies right in here. Okay, now let's go to our next table. Our next table has all of our Q's, Q stars, W's, and W asterisks. I need to calculate my fraction that's diverted. is H7 minus H6 divided by H2 minus H6. And when you calculate that for this problem, it does come in, like I've been saying, around 20%. It's 0.2046. 20.46%. Meaning 1 minus y is 79.54%. Okay. So what I would do is I would first calculate all the Q's and the W's per kilogram of what goes through each component. So through the reheat of the boiler, that's a change in enthalpy. That would be H3 minus H2. That's H3 minus H2. Through the condenser, we want that negative sign, so it's going to be the lower enthalpy H5 minus the inlet enthalpy H4. And then I do a little diagnostics on the boiler here, those three components. Okay. Now, for the boiler, we have this Q asterisk. This is what is per going through the first turbine stage. So you take the 601.1.7, which is our Q, multiply it by 1 minus y, because isn't that the mass fraction that went through the reheat? So that's the 0.7954, and that's what gives you a lower number. So per kilogram that goes through the first turbine, there's less heat added in the reheat. You have to think about it. But we're going to sum this column, and that column is really, everything is on the same per kilogram basis. If you sum this column and that column and compare them, they wouldn't be the same. But because we conserve energy and we put everything on the same per unit mass basis, this column and that column will have the same answer. Okay. How about through the condenser? Same thing. You multiply that times 1 minus y, because not everything goes through the condenser. All right. But through the boiler, these are the same because the first pass through the boiler is everything through the first pass of the steam generator or boiler goes into the first turbine. This one plus this one plus this one plus that one is that one. So I just take this one and that one and there, sum them, and I get 1163. Yeah, I think that's right. All right, so this basically tells me all of the heat came in. Everything is 2,954. I can go back and take a look, and in the reheat, 16% is what comes into the system, 18% to heat up the fluid that's still cold up to its boiling point in the first pass, 49% is to make it boil in the first pass, and then 17% is to superheat in the first pass. So that's why I have these extra numbers. Okay, what about the works? Same thing. Notice that the works of the pump, I make them negative so that when I sum in this column, it's correct. And the work that goes through the second pump is 100%, but it's 1 minus y that goes through the first pump. And it's 1 minus y that goes through the second turbine, but it's 1 times the first. So this difference between the work that goes through the first turbine versus the work through the first turbine per kilogram that goes through the first turbine, they're the same. And likewise, these are the same. But now I put everything here on the same per unit mass basis. These match. Make sense? All right. So let's continue on with, I think, the last slide that I have to show you. And it's a summary here. I didn't put in the TS diagram. But once I have my table of properties, my table of energy transfers, and I can then calculate my backwork ratio and my thermal efficiency. How do I calculate the backwork ratio? It'll be, I know I have to get rid of the negative, but I'll sum those two, and I'll divide it by the sum of the turbine output. So the backwork ratio is the negative of the negative 7.9 plus negative 0.8 divided by 498.5 plus 673.2. And you'll get that it's a very low percent. It's 0.74%. That's great. And then the thermal efficiency. How do I get the thermal efficiency, eta, for the plant? Well, it's our net work out. Is that my 1163? Yeah, isn't that it? Divided by what came into the working fluid. Into the working fluid would be the sum, because I calculated that right here, 2954. If you have a calculator, can you verify some of these, either both of them or one of them? Okay, the efficiency is definitely correct. And the backwork ratio is correct. Thank you very much. Well, that was a lot to cover. And I hope I didn't put you to sleep at the end. Because when you watch me do it, it's not as exciting. But you need to be able to do it, okay? So I'm going to stop at this point. If you have any comments or questions, come up and ask me. Thank you very much for your attention.